For our first example, let's look at the sine function. I usually see people using the sine function to create a smooth waveform like the one I have here. I've created an emitter, set the particle's max count attribute to 30, which limits the number of particles in the group, and added this creation expression. This offsets each particle in x by 1 unit. I'm also declaring a per particle float called rand_y that I'm going to use in my runtime expression. This animation is rather uninteresting unless you've been given the task of animating a sine wave. In the runtime expression, I extract the particle's position into a vector variable, then modify its position in the y-axis with a float that equals sine of time times 10. I add the particle's ID to the equation to get a more interesting offset in the animation. Remember, if I add a multiplier to the variable $pos_y, I'm changing the amplitude of the wave. If I change the number that evaluates inside the sine function's parentheses, I'm changing the frequency. Drawing relationships between the two can help you fine-tune your animation without too much guesswork. I can make this animation much more interesting by layering a number of these sine functions over top each other. This animation has a much more random feel, despite the fact that each particle is still moving at approximately the same speed. I can further randomize this simulation by adding 2 more random floats to my creation and runtime expressions. Now each of my particles moves at a different speed. I could take this expression much further by adding different per particle floats for any of these multipliers, by modifying the time evaluation, etc. One could go so far as to create your own emission pattern using this technique. In the file fakeemitter.mb, I've used the same expression but multiplied it by the particle's age, so I get a cone-shaped particle emission.